Today I want to tell you about using transmission electron microscopy to understand materials synthesis. So in my lab, we do all our synthesis in solution, as many people do. And so we like using cryo-EM and liquid phase EM because it allows us to maintain that solution inside the microscope. And that solution is really essential for maintaining the structures that we want to image. Traditionally, these methods have been used in different communities, but from the materials chemist or engineering perspective, they're really complementary. So cryo-EM has this method of maintaining solution by freezing. And so what that means is your transient structures can be trapped. That can allow you to spend a long time to image them and get the highest possible resolution images. Liquid phase EM, on the other hand, of course, you're imaging your liquids at room temperature typically, and that allows you to make kinetic measurements and dynamic processes, something which is impossible to do with cryo-EM. Of course, one of the limitations here is that, motion blur, for example, is always going to limit your resolution in comparison to cryo. And so I think they're completely complementary in that respect, and hopefully I'll show you that a little bit today. So we investigate different types of materials in my lab, and they're all materials that can be formed through self-assembly, which is essentially where we take some building block that we've synthesized, we put it in a solution, and we allow it to kind of organize itself by controlling the conditions of that solution. And today I'll tell you about 3 different projects that we work on: polymerization-induced crystallization-driven self-assembly, liquid-liquid phase separation, and protein-metal-organic frameworks. The goal in each of these, I will say, is to understanding something fundamental about the mechanism that enables us to redesign the self-assembly process such that we have better control over the structure of those final materials. So the first story I want to tell you about began really when I was doing some liquid phase EM studies on vesicle formation. So here I'm going to show a movie of polymer vesicles forming with liquid phase electron microscopy. And when I was investigating this movie, we found something that we didn't expect to see. So this image here is what we call a cross-sectional time series. So we take each frame in the movie, we crop out an area where a single vesicle forms, we take a line profile down the center of every one of those images, and we play all those line profiles as a time series so we can look at the continued evolution of this structure with time. What we see is in the very beginning of this movie, the vesicle forms from a low contrast, large structure. And so our inference from this was that this first stage in the formation should be some kind of solvated polymer-rich liquid droplet. And that's in contrary really to the mechanisms that people had proposed previously, where the first stage should be the formation of a spherical micelle. So in the last couple of years, my grad student Arn's been investigating that quite a lot, and he's managed to identify and isolate these liquid phase precursors in many different types of polymers. Here I'm showing PEO-PMMA. And this is an optical microscopy movie of some of those liquid droplets undergoing dynamic processes. And so actually in the kind of coacivate literature, these polymer-rich droplets are often called coacivates. Some of the most definitive evidence that people use for determining that these are coacivates is a visualization of the dynamic processes that they're undergoing. So fusion of droplets and the motion of these liquid droplets. And you can see they kind of flow like a liquid and they don't flow like a solid. So that's why liquid phase electron microscopy comes in really handy, because it allows us to make the same kind of dynamic measurements. And here we can see these same droplets, but on the nanoscale, again, undergoing flow and fusion like dynamic processes, which are indicative of liquids rather than solids. So identifying these liquid phase precursor droplets has been really important in understanding how we can control the size of the solid polymer particles that we get out in the end. So what Arn has showed is that if you have nanoscale liquid droplets, you can get nanoscale solid particles by simply adding water to change the phase behavior. If you have micron-sized liquid droplets, you can get micron-sized polymer particles. And you can even macroscopically phase separate this system. So you have a liquid layer here and then a liquid layer at the bottom. Again, you can add water and convert this into a macroscopic polymer particle, which if we look at it under SEM, has this hierarchical porous structure. So this is a phase diagram that Arne produced that shows how you can control this phase behavior by the addition of water. And what we see, in blue here, we have the region where these liquid droplets form. In many cases, it's a very small region, so it's only a few % of water. And that means it's a small region of the phase space, but what we can see here is that it's a really important region of the phase space, because if you know where it is, you can stabilize those droplets and change the size of the structures you make over many orders of magnitude. So that kind of control is something that's really hard to obtain with conventional methods. And here our kind of understanding of these mechanisms, our understanding that these liquid phase precursors are present is a really important part of controlling these. Okay. Story number 2 I want to tell you about is ring opening, polymerization-induced, crystallization-driven self-assembly. This is a method that my graduate student Paul developed previously. So very briefly, in the previous example, we were forming these nanostructures or microstructures or macrostructures by first synthesizing our polymer in one step, and then in a second step, assembling it by doing this solvent switch. In this example, we're going to do everything in one pot. So we're going to make our polymer. Self-assembly is going to occur simultaneously. So that occurs when you create a situation in which the polymerization conditions are favorable as well as the self-assembly conditions. And in this specific case, we're actually doing self-assembly by crystallization. And so everything occurs in a single pot. What's kind of unique to the system that Paul developed here is that the self-assembly and crystallization is very slow compared to the rate of polymerization. So what you can see here are some kinetic measurements. Essentially, we're looking at the change in turbidity of these solutions versus time post-polymerization. And what we see is there's a lot of growth and evolution of these structures after the polymerization finishes. So that's really unique actually to these kind of polymerization-induced self-assembly processes. I think in all other cases in the literature, structural evolution occurs only as you're growing the polymer. So what that means is that in most PICDSA processes or in all other PICDSA processes, the only control you have over polymer structure, over the morphology, is the polymer structure. So if you want to make a different morphology, you have to make a different polymer. Whereas what Paul has shown here is we can add an extra dimension to this, which we can control the structure with also time post-polymerization. That's what I'll show you in the next couple of slides. I'm not going to get into it today, but we also believe we can control the structure with the rate of the polymerization as well, but that's something for another day. So in these PICDSA processes, producing these phase diagrams is a very common thing to do. So the phase diagram shows us the different types of final structures we get as we vary, say, the concentration of our polymer in solution, or some structural feature of the polymer, like the degree of polymerization of one of the blocks. And Paul's done that, and he's shown that we can form a variety of different structures, 1D structures such as spheres, 2D structures such as lamella, and 3D structures such as these stacked lamella, which actually eventually form gels in solution. And here we can see some we can see a cryo-TM image of some of the lamella. So you can see here we have these kind of micron-sized lamella, which have a nanoscale thickness. These dark lines here are actually the lamella rotated on their side, and you can see they're starting to stack up here. And some of these examples in the kind of top right corner, this stacking leads to the formation of these macroscopic materials which gel the solution. If we freeze dry them, we see we again have this kind of hierarchically porous material, which is really interesting for many applications. But as I said on the previous slide, Paul also showed that time is a really important factor here. So this phase diagram is kind of the final structures that you produce, but every one of these individual points, you can trap out many different structures by freeze drying the samples at different stages after the polymerization. And I just want to tell you 2 completely different mechanisms that Paul found, which allow you to make different types of structures. So all these cryo images are taken post-polymerization. And what we can see for this specific system is that we evolve from having spherical particles to forming these rod-like structures. And then these rod-like structures align to form these quite well-ordered lamella, but they're kind of a halfway house between lamella and rods, as you can see here. So this mechanism, we believe, occurs actually is a kind of self-templating mechanism. So in the beginning, we think they form these very thin fibers, and those fibers template the place where the spheres and rods and lamella will eventually grow. So it might not be super clear in those images, but yeah, in this higher magnification image here, we can see in the background these very, very thin fibers that are templating the growth of these rods. In the bottom and top here, you can see ice contamination. And what you can see from the ice contamination is these are extremely defocused images. And it was really essential to have that high defocus in order to be able to view these fibers, because they are so thin and low contrast. It was extremely difficult to observe them, and something I don't think you would observe at all in liquid phase electron microscopy, at least without significant improvements in that technique. A completely different mechanism that we observed for a different polymer is actually a fusion-based mechanism. So in the early stages of this formation process, what we find is these kind of irregularly shaped spherical or rod-like particles. They evolve to form lamella again, but the lamella here have a completely different look to them. They're much less structurally precise, I would say. And then they continue to stack in 3D as they did before, but this time with much more three-dimensional stacking. So what we believe is going on here is actually a aggregation-based mechanism that's consistent with the kind of structures that we're seeing with the lamella here. And we also believe this aggregation-based mechanism is the reason why we see more three-dimensional stacking here. So it was only, this mechanism was the only one that's responsible for forming the gels that I talked to you about before. And you can read more detail in the paper, but these different mechanisms are really controlled by the folding of the PLLA chains during the early stage of the polymerization. And so we believe we have a good handle on how to control this mechanism, and that's going to enable us to add this additional level of design in here. Then very briefly, I just want to tell you about the last project. So it's protein-metal-organic frameworks. There's a lot of work trying to stabilize enzymes with metal-organic frameworks to use them in the chemical industry as biocatalysts. One of the easiest ways to make these composites is just to simply mix all the ions together with the biomolecule in solution and have everything crystallize out. But if you want to design those, you really want to understand the nucleation and growth mechanisms. So we've been investigating that with cryo-electron microscopy. And what we found here is that everything actually forms colloids in the beginning. So here we can see, this is a cryo-EM composite image of one of these precursor particles. So in the middle here, we see this 7 nanometer particle. That's a BSA protein, and it's surrounded by this couple of nanometer shell, and that shell is a mixture of methylamidazole and zinc. They're the precursors to the MOFs. So we have this kind of amorphous precursor particle. What we find is those amorphous precursor particles actually adhere onto the surface of the MOFs as those are growing in solution. And we can also confirm that with XRD. So at the 30-minute time point, we have a mixture of a crystalline phase and this amorphous phase. At the end, after 24 hours, our final product is just purely crystalline. And yeah, what we believe is that this is a surface addition process. Crystallization occurs at the surface of these crystals. We also confirmed that with fluorescence microscopy, where we can clearly see the biomolecules located on the surface of these crystals. So in short, then, actually, what we intend to do now is kind of redesign the self-assembly process based on colloidal assembly principles rather than standard nucleation and growth principles. And we believe that in doing that, we'll exhibit much better control over the formation of these structures. So that was a very quick intro to some of the things we do in my lab. Just to reiterate, the general thesis of my lab is that if we can understand the mechanisms of how materials self-assemble, we'll be able to redesign the self-assembly processes to have better control over structural properties. So I'd like to thank everyone in my group and all my collaborators and everyone for funding. And thank you very much for listening to this presentation.